Hi everyone, my name is Feyza. I am a graduate student at Oregon State University working with Dr. Weiss and Dr. Ishkur. Today I will present our research on service life prediction of concrete against microbial induced corrosion. As a brief introduction, microbial induced corrosion of concrete is a multi-stage deterioration caused by the microbial activity in the wastewater infrastructures. It reduces the service life significantly, and it has a serious economical and environmental impact. It's a worldwide problem for us. So how this process happens is the sulfur oxidizing bacteria in the pipes uses sulfur compounds and produce biogenic sulfuric acid, and when this biogenic sulfuric acid reacts with the concrete, it produces ettringite and gypsum, which damage the concrete significantly. So the microbial induced corrosion has three main stages. Stage one is the abiotic pH reduction. The second stage is the attachment of the bacteria on the concrete surface and beginning of the acid attack. And third stage is the severe sulfuric acid attack. So there are different type evaluation methods. One is chemical tests. These tests are practical and economical, but there is no bacteria involvement in the test. So we can say these are realistic simulations. The other option is microbiological test. There is bacteria involvement. This is more realistic simulation, but the test parameters might vary a lot from lab to lab. And these tests are usually difficult to set up and operate, and they're time consuming. And we have in situ tests in the field. These are the more realistic tests, but it might vary, depends on the severe conditions, and these tests requires a lot of effort and time. So we have recently developed tests, ASTM C1904. This test has both bacteria involvement, so we can say it's realistic simulation. It's safe and accelerated, and it's really easy to set up and operate. The only disadvantage here, we don't know the relation with the field conditions since it's a new test. So our research question here, can we develop a service life model to predict field performance by using this ASTM test? So for that, first we should look into the other methods commonly used to predict the field performance. We have biological chamber test. This is common and realistic simulation, but again, these are really time consuming and difficult to operate it. And some researchers use field as a laboratory. They immerse samples or they take samples from the real severe, but these are difficult tests. And we have some empirical methods. Pomeroy model is one of the well-known and commonly used method. But Pomeroy model is not suitable if we have antimicrobial treatment or any admixtures in the system. So our aim is to predict the service life performance in the field with ASTM testing by using the Pomeroy model as an underlying theory. I will give a brief background for Pomeroy's model and ASTM testing. Pomeroy's model has an equation to predict the corrosion rate in the field by using different parameters. Here, K is the coefficient for the efficiency of the acid reaction. It depends on the engineering judgment. We have chrome corrosion factor. This depends on the location in the severe pipe. And we have turbulence corrosion factor. It might vary 1 to 10, and for high turbulent flow, we have higher corrosion rates. And we have Phi. Phi represents the average flux of the hydrogen sulfide in the severe pipes. This can be measured in the field, or we can use another equation, as you can see, with different parameters like slope, velocity, by using from Pomeroy's model. And last parameter is the alkalinity. This is the alkalinity of the material that we use in the field. So for the higher, due to inverse relationship, if we have higher alkalinity, we get lower corrosion rates. You can see from a study on the left. And we have a new testing method, ASTM C1904. this test is designed to test different stages of microbial induced corrosion for different mixtures, antimicrobials, and admixtures. We have option B testing for stage 2 and option C testing for stage 3. Basically, we have control samples without any bacteria exposure, and we have inoculated samples with bacteria exposure. And during our testing time, we measure the pH, calcium ion concentration, sulfate concentration, and at the end of the test, we apply B3B flexural strength test to find the strength loss and calculate the thickness loss and corrosion rates. So in our model, we start with a preliminary study to validate the Pomeroy model with a laboratory test. So we took some chamber test data from the literature and we calculated these with the Pomeroy model. On the x-axis on the left, you can see x-axis represents the measured corrosion rates in the experiments from the literature, and y-axis is the calculated corrosion rates we calculated by using Pomeroy's model. So we can see that estimation of the corrosion rate with Pomeroy model is approximate to actually experimental corrosion rates. And in our model, we will define different correlation factors to correlate the field condition and our ASTM testing. First one is to correlate the K factor. For ASTM testing, we immerse the specimens in the acid solution, so we can assume that K is 1 in the worst condition, but in the field, K is usually lower than 1, 0.8 is a good estimate. So our first correlation factor would be ratio of the K factors. And the second correlation factor will be ratio of the alkalinity, because in our ASTM testing, we use the paste and mortar samples, and in the field, we use the concrete. And the mixture type affects the alkalinity factor significantly, so our correlation factor is required for the alkalinity. For the third correlation factor, we will use to correlate the average flux in the ASTM testing and in the field. So in ASTM testing, we calculate our average flux, and in the severe, this can be measured or this can be calculated by using the Pomeroy model. So when we calculate all these correlation factors and apply this into the Pomeroy model, we can find the correlation between the field condition and our ASTM testing. And we can calculate an acceleration factor, but this depends on the ASTM testing here and the severe field condition that we are checking on. So here I will present some results. These are some mixtures we did for the ASTM testing. D0 here is the mix without an antimicrobial treatment. For D15, we have admix antimicrobial treatment. For D15C, we have admix and also we have a densifier. For D15T2, we have both admix and topical antimicrobial. You can see the corrosion rates and strength reduction at the bottom. So for the samples without an microbial, we have the highest corrosion rate. It decreases with the admix antimicrobial, and we have almost zero corrosion rate for the topical. And these are the parameters for a real saver data. So we can use these parameters to calculate the flux, and we know the acid reaction factor K and alkalinity factor here. So again, when we compared all the correlation factors by using our ASTM testing and by using the parameters from the field, we can find the direct correlation between the field conditions and our ASTM testing. And by using the corrosion rate from our testing, we can calculate the expected corrosion rate in the field. So here I will show some results. as you might remember, we had experimental corrosion rates from ASTM testing. So we can put these corrosion rates into our equation and we can calculate the expected corrosion rates in the field. First one is the D0 without any antimicrobial treatment. We see a decrease with the admixed antimicrobial treatment. And when we add densifier, we get lower corrosion rate in the field. And as I mentioned, we had almost zero corrosion rate for the topical one, but we defined a factor, delay factor here, because topical on the surface might be leaching. So after a point, our admixture might be losing their effects. So delay factor is something that we are still working on it. So as conclusion, the proposed service life modeling aims to provide correlation between the ASTM testing and field data by using the Pomeroy model. And we can provide this by using some correlation factors for different parameters. And the expected corrosion rate in the field can be computed for different mixtures or antimicrobials or admixtures. And we are working on to validate our study with more field study, and we are working on improving our correlation factors for different parameters, and we are working on the delay factor for the admixtures and antimicrobials. So thank you for listening, and I want to say thank you to Sam Lines and Conseil for supporting and funding this research. For questions, I will be happy to answer.